Kenta, we're going to look today at air resistance. Air resistance is a very, very difficult force. A running joke in physics is the most terrifying sentence in physics is include air resistance. When a question says that. Really? Okay. We're going to look at it in limited snapshot situations. We can handle that. To do it properly, you really need calculus. But here we go. What is air resistance? Air resistance is the force of air molecules bumping into an object that's moving through the air. Really? Can air molecules apply a force? That's really why I have the air Zuka. Did you feel a force? Okay. By the way, if air molecules can apply a force, does air have mass? Must. You take it for granted because you're used to the air pushing down on you all the time. But in the same way that deep ocean fish take for granted the massive pressure of the ocean pushing down on them, all of us actually live at the bottom of a vast ocean of air. We don't notice it because we've grown up that way, but it is always there. So air has mass. Here's the key concept that you want to underline. When we talk about, get the obvious one, gravity, what direction is the arrow on our free body diagram for gravity? Okay, what about the normal force? That was in the opposite direction of the surface at 90 degrees. For air resistance, its direction is always going to be opposite to the way the object is moving. So if you're asking, which way am I going to put air resistance? Which way are you moving? The other way. Example 1 says, draw free body diagrams for each of the following. A ball being thrown while it's in my hand. B, after it's left my hand on the way up. And C, after it's left my hand, but now on the way down. So we're going to do a free body diagram. I'm going to zoom in for Taya. Okay. So here's the first situation. What are the forces acting on it? Get the obvious one. Okay. Oh, by the way, did they give me pictures? I'm going to be lazy. Rather than do a separate free body diagram, I'll label the pictures because that's technically not a free body diagram, but sue me. So Ryan, what did you say? Which way? Okay. What else? Well, when I throw the ball up while it's in my hand, which way is the ball accelerating? Which way must there be a bigger arrow pointing then? Okay, so I know this has to be there. I'll exaggerate it to make it obvious. What is that? Yeah, it's kind of, you could call it F throw. You could maybe argue my hand is like a surface and call it a normal force, except typically a surface is flat and my hand holding it like this is curved. I'm going to call it F throw. Here's what I do know. F throw has to be bigger than mg. What if F throw isn't bigger than mg? Look up. Watch. Did the ball leave my hand? For the ball to leave my hand, F throw has to be bigger than mg because it's going to then continue going on its own momentum. Did it say in part A include air resistance? Then we won't. Because you could make an argument while my hand is moving up, there is some air resistance on it, but it didn't say to include it, so we won't. Ooh. Kenta, did it say in part B to include air resistance? All right. What are the forces acting on it in part B? Get the obvious one. Yeah. Which way? Yeah. All right. And it wants me to include air resistance? Which way is the ball moving in part B? Which way is air resistance then? Bigger, smaller, or the same size as mg? The answer is it depends. But I'm going to make the assumption that it's smaller, but it can be bigger and it can be the same. And we'll talk later on in today's lesson about when those cases occur. Ooh, Jazz and Deep, what about part C? Now we're on the way down. Okay, what are the forces acting on it? Get the obvious one. Which way? What else? Which way? Which way are we moving? Down. Air resistance is the opposite direction of motion, and I'm going to assume it's smaller, but again, there are situations where it could be bigger or the same. We'll talk about those. Diagram B is a little interesting to me. How can, in diagram B, how can the ball be going up when all the forces are pointing down? Or have we screwed up? How can the ball be going up when all the forces are pointing down? Is that a hand up? Oh, no. This is a very common mistake that kids make. They confuse two things. And I've kind of hinted at it, but this is really where we're running into it. Yeah? Yeah, right. Okay, here's the problem. Goes is not a physics word. Oh, Ryan, what? You just said a word under your breath. Okay, Newton's laws tell us nothing about velocity. Nothing. Do you know what they tell us about? Starts with the letter A. They tell us the direction of acceleration. They do not tell us the direction of velocity. So let's look at this. What direction is the ball traveling? Starts with the letter U. Is it speeding up or slowing down in picture B? So which way is it accelerating? Which way is my free body diagram showing an acceleration to be? Same answer. No problem. This is correct. But the key is to realize, in fact, this is what we'll write here. Newton's laws tell us A, not V. Put a vector sign above the A and above the V. I can't do that when I'm typing, but you can. They tell us the direction of acceleration. They do not tell us the direction of velocity. Now, usually, the direction of the velocity and the direction of the acceleration are the same. Not always. So don't confuse the two. I will try and get you with those in the future with little thought puzzles or Voti questions or things like that as well. I will tempt you to mix up velocity and acceleration. Newton's laws don't tell us anything about velocity. Oh, let's keep going. Cameron, if part C is speeding up, write a force equation. Oh. So since it's speeding up, they're really telling me I can assume F air is smaller. Who's winning? Who's losing? Who's losing? Equals? Yep. Okay. So what might I ask you? I'm not going to ask you to calculate air resistance using the air resistance equation. You can Google it sometime. You'll see it's pretty scary and complicated looking. It's got a V squared in it. It's got a rho, which is a Greek letter like that, which is air density. It's got all sorts of stuff. What we can do using Newton's laws is kind of figure it out with snapshots. So example 4, suppose the ball in example 2 has a mass of 2 kilograms. If air resistance is exactly 5.2 newtons, what's the acceleration in situation B? Okay, I can do this. Brendan, I've scrolled down. Look at situation B. Everybody? Who's winning? Your hint is, it's a trick question. Who's winning in situation B? Which way are we accelerating in situation B? Down. So which way is the winning direction? Same answer. Who's winning? It's a trick question. They both are. It's like elementary school sports day. Everyone's a winner! No losers! So what's my equation going to be? Anything that's a winner has a plus sign in front of it. So it's going to be winner plus winner. It's going to be mg plus f air equals ma. Brendan, what are we trying to find in this question? Oh, Sean's theorem. Right? Now we'll divide by m. It's funny. I'm so used to going winner minus loser that this morning when I taught this lesson, I put the plus sign here, but then in the next line I put a minus, and on my calculator I put a minus, and the kids called me, Mr. Derrick, it's plus. So just be really meticulous. A is going to be, well, let's keep going. Brendan, what's M? They told me in the question, I think, somewhere. 2. By the way, are you starting to realize why I told you it's worth memorizing units? I hope you're at the stage where you didn't look for the word mass, you looked for kilograms. And I hope, if it asks you for an acceleration, you're just looking for meters per second squared. You're not even looking for anything else. So 2, what's G? 9.8 plus F air is 5.2. That's in newtons. No need to multiply it by anything. Divided by 2. I should be able to do that in my head, because 2 times 9.8 is 19.6 plus 5.2. 19.6, 24.6, 24.8. Divide by 2, 14.7? No? Am I wrong? 12.7. No. 24 divided by 12.7. God, I could have showed off and I got it wrong. 12.4? Okay. I was way off. Units. Meters per second squared. Mr. Dewick, how can the acceleration be bigger than gravity? Look at the picture. Two things are slowing it down. Gravity at 9.8 and air resistance. You know what? I could have predicted that the magnitude was going to be bigger than 9.8, because now two things are slowing it down. Adam, what about in situation C? What's my equation? Which way are we accelerating in situation C? Who's winning? Same answer. Give me my equation. F air is pointing downwards in situation C? Here. It'll be that. Okay? Sean's theorem. Get the A by itself. In fact, you know what? I think the numbers are identical. I think if you backspace and just change the plus to a minus, I don't think anything else is changing. If you're lazy, go ahead. Seven point something, I think, but I don't trust my math anymore after botching it, the first one. 7.2? Does that make intellectual sense? In a vacuum, what would the acceleration be exactly as a number? 9.8. Air resistance is acting in the opposite direction, so now we're not accelerating at 9.8, a little less than 9.8. Yeah, that makes sense. Okay? If the question doesn't say include air resistance, don't. But if it does, okay. Air resistance, though, is a tricky force. How many of you have ever held your hand out of the window of a moving car, preferably not when you're driving, and you've done the air surfing thing, where you've kind of changed the angle and flown like an airplane? You may have noticed as you speed up, what happens to the force of air resistance? Yeah. As you slow down? So that's what makes it such a challenge. It's a changing force, which means a changing acceleration, which you really need calculus for. But, again, we can handle it in snapshots. For example, example 4. A 90-kilogram parachutist, I mentioned I jumped out of an airplane, free falls for a time and then opens a parachute. His new upward acceleration is now 1.5 meters per second squared. First question, why is this parachutist's acceleration upward? How is that possible? Moving down, but slowing down, acceleration is up. Yes? B says, draw a free body diagram. Okay. What are the forces acting on this parachutist? Get the obvious one. Okay? Which way are we accelerating? Which way is there going to be a bigger arrow pointing? What arrow is that? Let's call it F air. You can call it F drag, but yeah, I'll call it F air. I'll exaggerate it so it's stupidly obvious. Sean, who's winning? Losing? Equals? What does winner minus loser always equal? Okay. Sean, what are they asking me to find in part D? Which one? Okay. So if you'll notice in the previous question, I gave you the air resistance and I said find the acceleration. Here, I'm giving you the acceleration and saying find the air resistance. As I've said several times, as far as I'm concerned, if I show you how to do it one way, I can reverse the question in the other direction for forces. Yeah. How would I get F air by itself in the equation that you gave me? How will I move the mg over? Why? You're right. Because what's the mg doing to the F air right now? Okay? All that formula manipulation stuff coming in handy. I hope you're also at the stage, maybe if you're taking math this semester, where you found some of the formula manipulation stuff handy there too. So you're going to, Sean, am I correct? You're telling me F air equals mg plus ma or ma plus mg? I've scrolled down, Sean. What was m? Good. Hopefully you just look for kilograms, right? G, 9.8 plus 90. I've scrolled down. What was A? Don't need to make that negative or positive. I took care of all of that with my winner minus loser. How big is air resistance? And give me the whole answer, because I think it works out to 4 sig figs or something like that. 1,000? 1017? Real? Yep. Newtons. By the way, in this question here, am I speeding up or slowing down? So what would happen to this arrow as I slowed down? Would it get bigger, smaller, or stay the same? Smaller and smaller. Eventually, it will reach a point where it's exactly the same size as gravity. Does anybody know what we call that? That's terminal velocity. Terminal velocity is when you reach the point where air resistance and gravity are the same. It happened twice when I jumped out of an airplane. When I jumped out of an airplane. The first time when I was in free fall without a parachute, I hit a much higher terminal velocity because my air resistance was much smaller. The second time after I opened a parachute, I hit a new terminal velocity. So when I jumped, well, you know what? The physics of skydiving is quite interesting. I wrote here, the force of air resistance is actually not a constant value. The force gets larger as speed increases. A falling object will eventually reach a point where the force of air resistance equals the weight. Oh, what do I mean by weight? mg of the object, and it will hold a steady speed called the terminal velocity. Put your pencils down, look up. This is a pretty nice video looking at the physics of skydiving. And I like, they're very careful and they get it right.
When a skydiver jumps out of a plane at 3,000 meters, her speed goes through some big changes. So what's happening to the forces as you fall through the air? The force of gravity is always trying to pull us towards the Earth.
What are the forces acting on the skydiver right now? Get the obvious one. Are they accelerating down? Are they accelerating down right now? Say no. Are they accelerating up?
Oh, right now.
Right now, at that moment in time, I think forces are balanced. So what force is pushing up? This would be the normal force from the floor of the plane. Okay?
Before the skydiver jumps, the floor of the plane provides a counterforce, which balances the downward force of gravity, right up until the moment she steps out.
Which force is going to vanish now? Okay, so you're going to have mg. Right when she starts to fall, because she really hasn't started moving yet, air resistance is 0. But as she starts to speed up, what's going to happen to air resistance? Jazz and Deep, I want you here. What's going to happen to air resistance? So normal force vanishes, but then a new force, arrow pointing up, is going to kick in and get larger and larger and larger until it matches gravity.
Gravity immediately pulls her towards the ground, and she starts to accelerate downwards. But air resistance is acting in the opposite direction. The faster she falls, the greater the air resistance.
Under nerd trivia, you don't need to memorize this. I won't test you on this, but if, like me, you're a nerd who likes to know obscure trivia, terminal velocity is right around 55 meters per second for a human being. A little more than 50. Oh, On your calculator, can you go 55 times 3.6? Would you want to hit the ground at that speed? How many kilometers per hour is it? Okay. It is survivable occasionally. We have had people that have had, parachute mishaps and still survived, but rarely without permanent injury. Usually around now, someone asks, Mr. Dewitt, what's the record? As far as I know, there was a Russian stewardess in the 1970s. Her jetliner depressurized, and she got sucked out from about 33,000 feet. So about 10,000 meters. At that altitude, she blacked out right away because there was little oxygen. She did survive. We think she survived because she landed on a steep slope covered with snow, which kind of helped both cushion and make the impact last longer. We also think there were some trees that maybe acted a little bit like cushions and broke her fall. Now, she survived, but I don't think she walked again. She survived, so you can survive an impact like this, but maybe this is Captain Obvious. Don't jump out of an airplane without a parachute if you can at all avoid it, right? Okay.
Eventually, the upward force of the air equals the downward force of gravity. When forces are balanced, the speed remains constant. That doesn't mean she stopped falling. It means she stopped accelerating.
Don't confuse acceleration and velocity.
She's still doing a steady 55 meters per second, and hitting the ground at this speed isn't a good idea.
She's about to pull her parachute. Which arrow is going to get bigger? Which way? Okay?
To slow down, the upward force needs to be greater than the downward force. When the parachute's open, air resistance suddenly becomes much greater than gravity. The forces are no longer balanced, and this changes her speed. She slows down. Because she's slowing down, air resistance decreases until it balances gravity again, and she reaches a much slower constant speed.
5 meters per second is a much safer terminal velocity than 55 meters per second.
Approaching the ground at 5 meters per second is a much better idea.
Yep. Oh, when she hits the ground, which way will she accelerate in coming to a stop? Think about it. When she hits the ground, what direction will she accelerate in order to come to a stop? Ryan, which force is going to get bigger then? The one pointing upwards. For what's causing that? That's the normal force. That's the ground preventing her from sinking into it like quicksand. So we should see that red one spike.
As she hits the ground, there's a thumping great counterforce from the Earth, which decelerates her very quickly. So for skydivers to land safely, they need to understand forces and use air resistance to slow themselves down.
So I talked about free fall in kinematics, but now we're looking at it in more detail. Still the same stuff. We can explain a bit more. Yep. Were you here late? Hustle back, but next time I'll keep you here. I've now given you enough tools, free body diagrams, Newton's laws, winner minus loser equals MA, that I can throw completely random questions at you. And Jazz, as long as you don't panic, you should be okay. Jazz, look at example 5. What are they asking us to find? You have it in front of you. You can read in front of you too, you know. I have no idea how to do. You know what? This is probably a good job for her. Let's try that. There's the helicopter. What are the forces acting on the helicopter, Jazz? Get the obvious one. Okay. What else? So there has to be a bigger arrow pointing which way? Okay. What force is that? I'm going to guess maybe that's the lift force that they're wanting me to find, because I think that makes sense. It's what's lifting the helicopter. So I'll label this F lift. You could also call it F air, because it does say lift force by the air. But again, my point is I can figure this out, because now who's winning? Who's losing? Equals MA. What are they asking me to find? What am I going to get by itself then? Same answer. How? Yeah. Okay. What I'm not going to do is panic, freak out, or leave it blank. Good free body diagram. Again, because this is why I've been teaching you, get the obvious one first. You can see it would be tempting for a student, I've got to figure out where lift force goes. No. Put gravity in first, and then it becomes way more obvious. It's got to, you tumbled onto it right away, Jazz. You said, it's got to be a bigger arrow pointing up, Mr. Dewick. We're accelerating up. Okay? It'll be MA plus MG. What's M? 5,500. A, 2.5. 5,500. G, 9.8. Jazz, what'd you get? It's going to be pretty big. Probably 16,000, 17,000 range. Oh, wow, I'm way, sorry, what was it? 67,000? I said 60 and I was way off. 67,000? What? 67650? Is that right? Okay. My math skills today are like yours. Nearly non-existent, right? Hey, we could even do a little rocket science. A rocket which weighs 12,740 newtons on Earth is launched. The force of propulsion is 15,400. All right. Gurtej, what does A want me to find? Isn't it 12,740? Why can't that be the mass? What are the units next to that 12,740? What are the units for mass? So it can't be, I will deliberately try and snag you with this. Don't be telling me the mass is 12,740 newtons. Oh, what is this? This is the weight. This is mg. How can I find m? Divide by what? Yep. Okay, if I give you the weight, you actually know the mass. You have to type it on your calculator, but whatever. So it's going to be the force, or weight, to 12,740 divided by 9.8. What's the mass of this rocket, Gurtej, my friend? It should be around 1,300 plus or minus something. Oh, even? Wow. I normally don't make things work out nice for you, but okay. Units, it's a mass. Good. All right, let's keep going. Let's do a little rocket science. When you grew up, you wanted to be an astronaut? No? Okay. The upward acceleration, what does it want me to find? Okay, acceleration. Am I going to use VI or VF? I see forces. You know what this is probably going to be a good job for? Yeah. Let's make an assumption. Let's make an assumption that the rocket has just left the Earth. Maybe it's a centimeter above the Earth. And what I mean by that is it's not sitting on the ground. There's no normal force. Okay? What are the forces acting on it? You know, which way? What else? Did the question say include air resistance? So no. In real life, by the way, yes, which makes in real life rocket science very tough. Okay? Remember I told you the Russian stewardess story. I had someone in my last class ask, could we calculate the free fall? I said, well, in real life, no, because at 30,000 feet, air is so much thinner. You're actually, if you're trying to include air resistance, it's thinner there. It gets thicker as you go. It's a really tough question to solve. So if they don't ask you to include air resistance, smile and walk away. What else? They told me the name in the question. Acceleration is not a force. I'm going to say that's a bad guess. They told me the name of the force in the question. Yeah. Propulsion. See it? F prop. The other way you'll see this sometimes referred to in rocket science is thrust. You might see F thrust. But that's the tug of war, okay? We're getting propulsion force up, gravity down. How did I know to draw it longer? Which way are we accelerating according to this question? So who's winning? Who's losing? Okay. What do they ask me to find? Can y'all look up for a second? Now that I've done one like this with you, I would have no problem skipping part A, not walking you through that you need to find the mass. I have no problem expecting you to realize, hey, I need the mass. He gave me the weight. I'll need to divide it by 9.8. I will not walk you through that first step anymore. I did it once. We're getting the A by itself. Sean's theorem, right? A is going to be F prop, 15,400 minus mg. I was going to go 1,300 times 9.8, but I could also just go 12,740, because that's what mg is, divided by 9.8. Oh, divided by m. What did I say? 1,300. I looked at that, not that. That was silly. Thank you. What do you get? Round it off properly? 2.05? And meters per second squared. Okay. Let's do a little more rocket science. Suppose we had the ability to take this rocket and launch it from the moon instead. Suppose we moved the rocket to the moon where the acceleration due to gravity is only 1.6. If we want the rocket to accelerate up at 3.5 meters per second squared, how much force of propulsion do we need from the engine? You know what? I think it's the same free body diagram. In fact, I think it's the same equation, F prop minus mg equals ma. But, hey folks, what do they want me to get by itself this time? Oh, how? Add the mg over. So it's going to be F prop is going to be ma plus mg. M was 1,300. A was 3.5. Plus, I can't type 12,740 because that was mg on the Earth. Here, it's going to be 1,300 times, what's g on the moon according to this question? 1.6. How much thrust propellant, or how much propellant force? How much propulsion do you need? Kelly, would you? 6,630. You'll notice way less than the 15,400. This is one of the reasons NASA is sending rockets to the moon. If we do ever start to try and colonize the solar system, it would be way more economically feasible to do it from a moon base, launching our rockets from the moon, not launching our rockets from the Earth. It would be way more feasible if we get a permanent colony there that can do things like mine metals on the moon. There are some, to build the rocket. And then we have found water on the moon. Water is rocket fuel. Use electrolysis. You split it up into hydrogen and oxygen. Some of the best rocket fuel in the universe. Like that, and away you go. So hopefully in your lifetime. Turn the page or next page over. We don't always need to do, Taya, what does FBD stand for? Okay. Taya, what's example 7 asking me to find? The what force? The what force? The what force? I'm not doing that to make fun of you. This is a trigger phrase. If you ever see the phrase net force, what I'm saying is I've done the free body diagram already. I've done all the numbers. You can go straight to F net equals what? MA. So why? I've taken care of everything for you. Okay? So, what does this want us to find, Taya? I would go straight to F equals MA. What's the mass? What's A? Oh, did they give me the acceleration? Even though I'm supposed to find F net, you know what I'm going to spend most of my time finding, I think? Acceleration. So let's continue reading through. What else do I know, Taya, that I can use to find acceleration? What else? What's VI? How did you figure that out? Oh, from rest. And then VF is 33. Looking for an equation that's got an A, a T, a VI, and a V. There is one. Get the T by, or sorry, get the A by itself. Which equation, Taya, my angel? Yep. Since VI is 0, I'll probably skip writing that from now on, but I usually leave it in there the first time when I'm rearranging stuff. Yeah. So it's going to be 33 minus 0, I'm not going to bother writing that, divided by 8.5. What's the acceleration? I get 3.88235 and change. Okay. I'm going to write 3.88, but you know I'm going to use my answer button. And I'm just going to walk it over to here. F is going to be 1200 times my answer button. I'll even write ANS because I'm using my answer button. And I get 4,600 and I'll go with 3 sig fig, 60, I don't know. 4,660 newtons. 4,659. So I don't always have to do a free body diagram. If I see the phrase net force, go straight to F equals MA. All right, I've lied to you. Pretty much everything I've been teaching you the last couple of days is a lie. Tension is not a force. Normal force is not a force. Friction is not a force. In fact, there are only 4 fundamental forces in the universe. There's what's called the strong force. That's what holds the protons and neutrons inside a nucleus of an atom together, because normally like charges repel, the protons would repel each other, the nucleus would explode. There's what's called the weak force. The weak force explains radioactivity and a few other things. There's gravity, although we saw last unit, general relativists would say gravity's not a force, it's a curvature of space-time, but we'll pretend it's a force. There are some physicists, though, who would say there's only 3 forces. Everything else is electromagnetism. It's like charges repel, unlike charges attract. Do me a favor. Push down on your desk with your hand right now. Try and push your hand through the desk. Can you feel it pushing back on you? Now, we've called that the normal force, and we will still continue to call that. But if you want to know what's happening really, the electrons in the outer edge of the molecules in your hand are being repelled by the electrons in the outer edge of the molecules making up the table because like charges repel. We're not going to dive down to that all the time. So I have lied to you in that tension's not a force. That's the electromagnetic force of the molecules holding the rope together. Normal force, not a force. That's actually like charges repel. So I always point that out, but whenever it says hashtag nerd trivia, that's my way of saying I'm not going to ask you this on a test. This is me feeling guilty that I've taught you something that's technically incorrect. Okay? Yeah.
What's it called? Normal force, though?
It always pushes up at a right angle from the surface. And in math, there are 4 ways to say right angle to. Perpendicular, we could have called it F perpendicular. Normal means at right angles to, so that's why it's called the normal force. Orthogonal means at right angles to, and at right angles to means at right angles to. So they chose to go with that one. I'm going to guess the reason is there's probably a Latin word that worked better, because a lot of this comes from terminology that Newton and a few people that followed after him gave us, and he did most of his stuff in Latin. It's a good question. What's your homework? It's going to be easier to tell you to cross out questions. It means I'm giving you a lot again. I'm going to get there, but first I'm going to give you the homework. Can you cross out number 8, please? You can skip it. You can cross out number 13, please. But you'll have all day tomorrow to work on lessons 2 and 3 and 4. Yes, I know there's a part 2 of a video that we started watching the other day.